some very special components of the universe which totally defy our basic concepts of reality. And yet, they do exist. Stars are born, live out their lifespans, and die. The life history of a star is marked by two opposing types of pressure. One is the pressure created by the energy in the core of the star, pushing the surface outward. The other is the crushing force of gravity pulling the star's surface inward. When these two pressures are balanced, a star becomes stable and shines steadily. As hydrogen fuel is depleted, the release of energy is insufficient to withstand the gravitational pressure, and the core collapses. But this collapse heats the hydrogen still burning in a thin shell surrounding the core. The excess energy released lifts the outer zones against the force of gravity. The star is now a red giant. In the final stage of its evolution, the mass of a star determines its fate. The Sun, a medium-sized star, remains stable for approximately 10 billion years. Then it will expand to 400 times its present diameter. As it expands, it will engulf the inner planets, Mercury, Venus, Earth, and Mars, and create a nebula extending past the outer planets. After millions of years, its reserves of nuclear fuel will be exhausted. Its outer layers will have dissipated, and only a white dwarf star remains, no larger than the Earth. Slowly cooling to zero temperature, it will end its life as a black stellar corpse. When a star more massive than the Sun reaches the red giant stage, the collapse of its core raises its temperature billions of degrees and can trigger a spectacular detonation, a supernova explosion. At the center of the explosion, a residue of the star is crushed by gravity to a neutron core, only a few miles across, but so dense that 10 billion tons of its matter would fill only a tablespoon. It spins rapidly, generating radio signals in its strong magnetic field, a radiation beam sweeping past the Earth and observed as a pulsar. An even stranger end is predicted for the most massive stars. According to the laws of gravity as presently understood, nothing can stop their collapse. The star disappears from our universe, leaving a black hole in space-time. Its presence can be deduced only by its influence on a nearby object such as a visible companion star, distorted out of shape by the black hole's gravitational attraction. Gas pooled off the visible star circulates about the black hole and in a dizzying plunge emits X-rays which can be detected in space. No light or matter can ever leave the intense gravitational field of this cosmic abyss. The physical laws that govern the conditions within this bizarre object are practically unknown.
Black holes are one of the newest phenomena that have come out of astrophysics, and they come in many different sizes, large and small, and they are revolutionizing both astrophysics and relativity theory and the way we think about things. A black hole originally was thought to be the end state of a very massive star. When a star collapses, as it uses up its fuel, it no longer has light pressure to keep it blowing up. It falls down, and finally, the material in the middle gets so compressed that the electrons are forced back in to the protons. turning them into neutrons. The neutrons keep falling in, and finally the neutrons are right next to each other, and the nuclear repulsive force tries to push them apart. Now, if the star is small enough, that's what happens. They do repel each other with enough force to cause the explosion to stop. There's a rebound, and that's what causes a supernova explosion, leaving behind a neutron star core. However, if the star is bigger than about 2 solar masses, as the neutrons get pushed together, there is this repulsive energy. It's like pushing a spring together. You now have spring energy, let's say, stored in those neutrons. Now, energy, according to E equals mc squared, is another form of mass. And so we now have a little more energy, a little more mass in those 2 neutrons. The extra mass creates a little more gravity field, which pushes the neutrons a little closer together, makes a little more energy, a little more mass, and makes the gravity field stronger. And when you analyze it mathematically, you find that it is unstable. They will continue to collapse because the more they try to resist, the more gravity field they make, and the only result is in the description is the fact that they will warp space up on themselves and form what is called a stellar-sized black hole. And this is a typical black hole.
The reason the force of gravity is so immense in the vicinity of a black hole, as perhaps we find, say, in the binary star system, Cygnus X1, well, it's because the mass is so intensely concentrated. Now, even though the gravity is immense near a black hole, this doesn't mean that a black hole is some kind of a cosmic vacuum cleaner that sucks everything up that happens to stray within a few hundred light years of it. Actually, it's easy to understand why that's so by keeping in mind how gravity works. You can think of it in terms of a person, say, standing on the surface of the Earth. That person feels a force due to the gravity of the Earth, and that's just the person's weight. Now, we're normally about 4,000 miles from the center of the Earth's radius. If we take a person who weighs, say, 200 pounds, and then enlarge the Earth